Now let's take a moment and compare some names of ionic and molecular compounds. The two types of compounds are named using different naming systems. Using counting prefixes is reserved for molecular compounds. Even though counting prefixes make some sense for ionic compounds also, their use is generally reserved for molecular compounds. BaCl2 is an ionic compound. Its name is barium chloride, not barium dichloride. The use of a counting prefix for this compound is incorrect because ionic compounds, metals with nonmetals, are not named using counting prefixes. CCl4 is a molecular compound. Carbon and chlorine are both nonmetals, and in fact it's a binary molecular compound made of only two types of nonmetals. So this one should be named carbon tetrachloride using counting prefixes, not carbon chloride, because it's not an ionic compound. The use of the counting prefix is correct in carbon tetrachloride and incorrect for the ionic compound barium chloride. So ionic compounds and binary molecular compounds are named using different rules. That means it's important to pause, take a look at a compound, and first decide which type of compound it is. Next, name the compound according to the rules for that specific type of compound. So let's give that a try. Here's a compound. Calcium's a metal, bromine's a nonmetal. That makes this an ionic compound. Since it's an ionic compound, we just name the positive part, and the negative part, and the use of counting prefixes is not acceptable. Calcium is a predictable charge metal, always taking or almost always taking the charge +2. This is an appropriately formed compound, and we simply call it calcium bromide. While it would be convenient if ionic compounds also used counting prefixes, that simply isn't the way they're named. Here's another one. Nomenclature that you see at the top of this slide is just a very fancy name for naming. So let's try naming this next compound. It has copper in it and oxygen in it. Metal and nonmetal makes it an ionic compound. Copper is a variable charge metal. You'll find it in the middle of the periodic table in the transition metal region. Since it's a variable charge metal, we're going to have to tell people in the name what charge the copper is taking in this specific compound. To be able to figure it out, we have to count on oxygen behaving in a predictable manner. Oxygen is predictable and usually forms the O2- ion. Since this whole compound overall has a charge of 0 or neutral, each copper which is present must be +1, because 2 coppers then would be a total of +2. -2 for the oxygen adds up to no overall charge. That means this compound is made out of copper 1 ions. So the correct name for the compound is copper, Roman numeral 1, oxide. Copper often also takes a +2 charge, and this would be the correct formula for copper 2 oxide. With 1 oxygen and 1 copper, the compound has a copper with a charge of +2. So let's name a few more. This first compound has sulfur and chlorine present. Sulfur and chlorine are both nonmetals. This is a binary molecular compound with only two types of nonmetals represented. Since it's a binary molecular compound, we can use counting prefixes. The name for this one is simply sulfur tetrachloride. The next compound has nitrogen and iodine present. Nitrogen and iodine are both nonmetals. There's only two kinds of nonmetals represented, so this is another binary molecular compound, and we're allowed to use counting prefixes. We simply name it nitrogen triiodide. So what's this last formula? CO3, 2-. It's not a compound at all. Compounds have to be neutral in charge overall. This last species is a polyatomic ion. We don't name it like a compound. We don't name it like an ionic compound. We don't name it like a molecular compound. It's a polyatomic ion which has its own specific name associated with this specific formula. The memorized name for this grouping with this charge is carbonate.
We already listed the general characteristics of ionic compounds, but here they are again. Ionic compound properties come from the nature of the ionic bond. Ionic compounds tend to be brittle, and they tend to have specific crystalline structures. Ionic substances tend to be very high melting, and also tend to be solids at room temperature. Many ionic substances are water-soluble. Ionic compounds act as electrolytes when molten or in water solution. Electrolytes are any substance which conducts electric current due to free-moving ions.
Molecular compound properties are quite different than ionic compound properties. Molecular compound properties come mainly from what are called IMFs between the individual molecules. IMF stands for intermolecular forces of attraction, and we'll be talking about these more in the third unit of study. But these IMFs are one of the most important things in helping predict and understanding the properties of molecular compounds. Molecular compounds in general tend to be soft, powdery, or waxy when they are solid. They tend to have moderate melting points as opposed to the very, very high melting ionic compounds. Many molecular substances are liquids or gases at room temperature rather than solids like ionic compounds tend to be. As far as water solubility goes, there always needs to be more information. Some molecular compounds are water soluble, and many are insoluble in water. Molecular compounds are usually non-electrolytes when molten or in water solution. This means they do not conduct an electrical current since no free-moving ions are formed when they dissolve in water or when they melt. Molecular compounds tend to form molecular crystals with individual molecules which are weakly interacting with each other. The intermolecular forces of attraction, or IMFs, within a substance are very important in determining the properties of that substance.